In this segment, we do a few more examples of linearizing a function and linear approximation. So the idea is to uh, replace a nonlinear function by a linear function, and at least near the point of interest, we can hopefully get a reasonable approximation to the function value. Okay, so let's suppose that we want to find a best linear approximation for f at x equals 0 when f of x equals x squared plus x plus 1. So we need the value of the function at x equals 0, which is f of 0 equals 0 squared plus 0 plus 1, which is equal to 1. We need the value of the derivative at x equals 0. So the derivative of the function is 2x plus 1 from the rules that we have discussed. And now if we evaluate that at 0, we get 2 times 0 plus 1, which is equal to 1. Then our linearization formula is this. L of x equals f at x naught plus f prime of x naught times x minus x naught. Here x naught is equal to 0. So f of 0 is 1. F prime at 0 is 1 times x minus 0. And that simplifies to 1 plus x. Now if we approximate f of 0.2, f of 0.2 is approximately equal to L of 0.2, which is equal to 1 plus 0.2, which is 1.2. Let's try another function. F is defined by f of x equals 1 over x squared plus x plus 1. Let's say we wanted to estimate f of 1.1 using linear approximation. Well, I might have a bit of trouble trying to evaluate f of 1.1, but f of 1 is easy. Finding f of 1 and finding the derivative of f at 1 will be simple. Those will just be rational numbers. And then I can find a linear approximation near 1, and I can use that to approximate f at 1.1. So f of 1, by the definition of the function, is 1 over 1 squared plus 1 plus 1, which is equal to 1 over 3. The derivative of f at x is given to us by this reciprocal formula, minus the derivative of the original function divided by the original function squared, provided that the original function isn't taking the value 0. So that gives me minus the derivative of x squared plus x plus 1 is 2x plus 1, divided by x squared plus x plus 1 squared. And if I calculate the value of that derivative when x is equal to 1, I get 2 times minus of 2 times 1 plus 1 over 1 squared plus 1 plus 1 all squared, and that works out to minus 1/3. Okay, so now I have the function value at 1 and I have the derivative at 1, so I can find the best linear approximation at x is equal to 1. Okay, so the linear approximation is given by f of x naught plus f prime of x naught times x minus x naught. F of 1 was 1/3. The derivative at 1 was minus 1/3 times x minus 1. So now if I want to find L of 1.1, that's 1/3 minus 1/3 times x is 1.1 minus 1, and that's equal to 0.3. And the actual value is 0.30211 or something, and so I can compare the two values and they're fairly close. Okay. Now let's take a look at this function. F of x is equal to 1 over 1 minus x for x not equal to 0. And we want to linearize that function for x equals 0. So for very small x, for x close to 0, f of x is approximately what? Okay. Well, the function at 0 is 1 over 1 minus 0 equals 1. The derivative of the function at x is equal to minus, the derivative of 1 minus x is minus 1, divided by 1 minus x squared, which is equal to 1 over 1 minus x squared. Now, then if we take that derivative and we evaluate it at 0, we will get 1 over 1 minus 0 squared, which is equal to 1. And then the linearization at 0 is given as f of 0 plus the derivative at 0 times x minus 0. That's 1 plus 1 times x minus 0, which simplifies to 1 plus x. So for very small x, 1 over 1 minus x is approximately equal to 1 plus x. Okay, final example. I have f of x equals 1 over 1 plus 2x. Near x is equal to 0, I want to find a linearization. Okay, so you can do it like we did before. Find the function at 0, find the derivative at 0, do the linearization. But we can also use previous results if we have them. So f of x is equal to 1 over 1 plus 2x. That's equal to 1 over 1 minus 2x. So for if x is very small, minus 2x is also very small. So this is of the form 1 over 1 minus w, where w is small. And we said that that's approximately equal to 1 plus w. So 1 over 1 minus 2x is approximately equal to 1 plus minus 2x by our previous result, which is equal to 1 minus 2x. So sometimes you can use your previous linearizations to help you do a linearization, and you don't have to then take a derivative and so on. Okay, so that's it for this.